Hello there, welcome to another episode of solving problems and clearing up concepts in physics. Okay, so you encounter in Newtonian mechanics lots and lots of problems that involve pulleys. I'm going to address some of the main ones. So you have over here, you have one pulley system with two masses, an axle, and there's a support. So this is we're going to say rigid support. And you may hold the masses at some point and let go, and want to say where will be each mass at a later time. That will be one kind of problem. Okay, so this arrangement is goes by the name Atwood Machine. And you sometimes say initially when you do the problem, you say no friction at the axle and no mass. But we're going to say there is a mass here, and we'll say we'll take care of the friction here. So when your axle, and the friction will be all around the axle, right? So at each point of contact, and assuming there's all points of contact around the axle, then there will be a normal force and corresponding a corresponding friction force, and this friction will be rolling friction. And okay, so similarly, you can see that this rope that's going around, it must be, I'll assume that this does not slide off. There's no motion from the sliding. The motion is, the rope motion is tied with the rotation motion of the pulley wheel. Okay. So another assumption we'll make is no slipping of the string. Okay. So we will see how that affects. So we're going to do the whole problem. And so there's going to be rotation as well as translation of these guys. Later on, we can say, okay, what if mass pulley was mass 0, there was no friction, and we will not let go of this. If there is slipping of the string, then basically the motion of these two blocks somewhat decouple from the motion of the pulley itself. Well, and we want to maintain that. Okay. So that's we'll continue to have that. All right. Maybe in the future we might discuss, if you lost sleeping, what kind of problems I might encounter. How do I solve that problem? So how much sleeping, etc. Now, the three pulleys problem. This is a typical three problem. You can of course have many pulley problems, but this is one arrangement in which you can see there are three pulleys, and we want to see, if I start off, same question, I start with these three masses, say at rest, and let go, what is the subsequent motion of the pulley? Okay, these pulleys, and what's the subsequent motion of these guys? You can say this guy is M1, this guy is M2, this pulley is M3. And this radius may be R1, this radius may be R2, and this radius may be R3. And we're going to just, when we solve this problem today, we're going to just say, just for the simplicity, we can just call it R same. In all of these pulley problems, this thread or rope that's going around, so you might say mass of rope. We are going to, at least for the sake of simplifying this, And in a future video, we will say what happens if the rope is not massless. We're going to be much less than M1, minimum of M1, M2. It's much less than, so we can ignore the mass of the rope. One more assumption in all these pulleys I'm going to make is the whatever happening during the motion, the string is taut. So string is taut. So string was whatever length, and then when the masses got put on, the string got extended to some point, but that length is not changing during the motion, and its length does not change during motion. It might have changed when we are putting the masses on, but after I put the masses on, they are remaining the same. So those are some of the assumptions that go into it, and it turns out that this is a very critical assumption. That this is a very critical assumption, and it tells you there is a constraint in the system. If the length is not changing, then the motion of M1 and M2 are connected. Say M1 is going down, M2 is going up. Well, they're going to have to go about same, or exactly equal to each other, sleeping or no sleeping. If it's no sleeping, then that's also related to how much. Say this was going down, say example, and this was going up. Then if it's no sleeping, then the amount is going to rotate. How much is going to rotate, this angle is going to rotate, will be amount that distance. So if it goes this much, say this much down, and this guy goes this much up, and this guy, so the amount that rope unwounded, that distance at the rim, all of these distances have to be equal to each other. Just because it's not sleeping, the string is not sleeping. If the string was sleeping and wheel was rotating at the same time, then this relation does not exist. So that's the this no sleeping thing connects the motion of M2 and M1 with the motion of the wheel itself. Okay, so let's do this, work it out in detail. All right. Okay, so let's I moved some things here, so I will do this later, so let's keep this aside. So over here we need to be able to write equation of motion for this block, and for the pulley. So there are three things I need to write the motion. So I need to identify forces and also work, take some kind of a coordinate system that's inertial. So the step one is figure an inertial frame. So this is our choice, and there are many choices you can have. You can have inertial frame for each system if you like, or you can have one that you can use for each one of them. So let's see, you could have something like this. There's a one inertial system I can see, can be very convenient. So maybe this is the x-axis, and this is not fixed to the axle, it's in a space, and you can say, let's see, from there we can just say down, make it y, so that these guys have positive y values. And so if you do it right hand coordinate system, the z-axis is in thumb in. So that's the z-axis behind this screen I'm writing on. Okay, so this guy's coordinate will be x1. So this guy's coordinate will be x1, y1, z1, and you sorry about that, there was a phone call and I had to take that phone call. So I was in the middle of this thing where you can see that these motion of these two, x and z, don't move. So I mean, you can just say I just want to follow y1. So this is the motion, this just with this, and this one similarly y2 of t, and the motion of this would be maybe rotate like this. So the angle that it rotates by, so this will be so you have x and y, and you can see amount of this angle phi with time t, right? Okay, so what it is take a point of the edge of this wheel, and you can see that point rotating. So this the angle phi of t is the angular coordinate of that point on the wheel. You can just stick a tiny mass there if you like, and just follow its motion, and that should be the motion of this wheel. Okay, so let's work one thing at a time. So this M1, if you look at M1, you have to look in isolation, and you'll see it has a tension T, let's call it T1, and it's got its weight M1G, and y-axis is pointed this way, so that's where the j hat direction is. So write the second thing is to write all of this in vector form, right? So T1 is minus T1 j hat. This let's call it W1. W1 vector is M1G j hat. So that's what using j hat makes clear what the directions. T1 is a positive number, M1G is positive number. So minus j hat tells me opposite to the y-axis, and acceleration vector is just y double dot j hat. I always use this dot stands for ddt, and in many problems it doesn't make sense to use it, but sometimes you can just use a sub y if you want. Here a sub y will be sufficient, but when the systems are kind of coupled, using this dot really helps. Okay, here they're coupled, so it's, well, we'll just use it, acceleration of 1. All right, so write down ma1 equals to f, because inertial frame. If it's not inertial frame, we learned that this is not correct. You do some other way. Let's write this. The equation will be m y1 double dot. So just all of them j hat. So this is the y component. So this is equal to minus t1 plus m1g. So that's one equation. Now if you do the other, so let's do the other one. Second one is going to be very similar, right? This is T2 and this is M2G, and almost identical, and y-axis again y down, so j hat in that direction. So everything is the same way. So this is going to turn out to be M y2 double dot equals to minus T2 plus M2G is identical. Same, you can carry out this much for this mass. The problem is the wheel itself, and so let's do that out. The wheel itself, what we're going to get is very interesting. So the tension now, the T1 was that way when you look at the tension in there, it is pulling up and is pulling that down. So that's why if you take a rope, you can, both sides is pulls in. So so this will be, this tension T1 will be acting this way on the wheel, and there is an axle here. So this is outside body, the rope is outside body. So the other side, the tension will be down like this, straight down, T2. Then there is a weight of, this is my system, right? This, the one that, not the axle, but this will actually be acting at the center of this thing. So this is mg, so this is like weight, and because of this weight you are going to have on this, there will be normal. Let's do the normal in this color. There will be all this direction, there will be normal, and say if this was rotating this way, suppose this is rotating this way, then the friction, static friction is the one that's doing this rotation. So it's going to be, static friction would be over there, and if over there the static friction will be a different amount. At each point the static friction is different amount. This is kind of look, that's the friction on the wheel. Okay, so this is the normals are corresponding normals. There's a normal here, there's a normal here. These are by the axle. So these are, so there's a, let's call it the net of all of this normal, because the axle is not going this way or this way, you know. So the net of this normal is, you might say that's the net normal. So that's the net normal. So we can just call it normal one place. But the friction, we will take care of friction through the rotation, because this is a rotation and not actually a translation motion. Okay, so these frictions must, these frictions in the normals, they must all cancel out in the horizontal component. So they must cancel out there, and we don't really need to worry about it. It must cancel out because there's no acceleration that way. So this is the x direction and this is the y direction. So the rotation will be like I, and if I do this x to y, so if this is the phi, so phi double dot, this angular acceleration, I will be the eye of the wheel, equals to all the torques from all these forces. So talks about the axis. Axis is going this way. So anything that's anything that's on the axis or crosses the axis, those forces will not be will not contribute. So if you look at normal and weight, this is the all these normals, no matter where the normals are, all these, extend them backward, they're all going to cross at the axis. So weight is right on the axis, so torque is 0. Normal crosses the axis, all normals, not just this normal, but normal in any direction, and so torque of normal is all 0. But this friction force is actually it's all kind of adding up. So, but Fr, if this is the axle, and so there's a friction here, friction here, and there's a friction here, there's a friction here, there's a friction here. The axle is within this is the axle, and that's the part of the wheel. So those are the axle is applying those frictions on this, and this is the radius of the axle. So the friction is not on axis, so there will be torque, and we're just going to say torque from friction, and it's going to be just you'll have to integrate all of this, add up all of this force, every force times this radius of this thing. So this will be like sum of all these frictional forces at location say I, and if you break it into small pieces, and then radius of the wheel. So this will be the total torque. All right, so let's look at what is A. I will be a disk formula. I can use it. That will be half m, and this radius of the wheel, this r, big M r square, phi double dot, and the tau is just, I'm going to just write tau of f. So we're assuming this is positive, and so this is positive. Okay, so we had for the friction part, and I originally kind of got excited and I forgot about these other forces, the torques from these forces. So we are looking at k-hat direction using right hand rule. So torque from this will be this radius times this, but when we take a right hand rule, is going to be z direction. So that's going to be T2R, and going to be T1R. So it will be this equation, not I phi dot equal just tau f. You need this also. So I'm gonna include it here. So this is going to I is half mr square, and after using phi dot equals to this, you should have half m y1, this is y1 double dot is equal to tau f over r plus t2 minus t1. Okay, in the same direction. Okay, I need to clean it up, and we have these three equations, but we're not done, because actually because of no slipping and the length of the rope, these two constraints have to be taken into account. and they will give me two more equations. Okay, so now let's look at this constraint. This constraint will do one thing. The length of this will be same. So what's the length here? Length is this y1, this y2, plus what goes around there, so pi times r. So length equals to length, this is the length of the string, equals to y1 plus y2 plus pi times r. So this is called constraint. So this is one constraint. To use this in the equations over there, we can take two derivatives and say y1 double dot plus y2 double dot equal to 0, because this 0 gives me 0 and this gives me 0. So you can see the y2 double dot equals to minus y1 double dot. So we can just get rid of this, make it y1 and put a minus. So we got one variable, so y2 double dot equals to minus y1 double dot. So once we find y1 double dot, we can plug in and get the acceleration for the second mass. Okay, other one is a non-sleeping. So if it doesn't sleep, then the amount that so if this is rotating this way, then the phi will be increasing, right? If this is rotating, phi will be increasing. So imagine it was here and then that dot was here. So let's imagine we have this axis. At t equal to 0, I place a dot over there, and a little bit later time this dot is over here. So it goes that much phi. Well, then this guy was over here, and this much rope is unwound, so y2 has gone that much, it increased that much, and so this angle phi, so it says amount of phi that increased is equal to times r is on this arc, right? Must be equal to delta y2. So if this is positive this way, then y2 increasing is positive. Only then phi is positive. If y2 is negative, then if it's going up, then phi is going in the opposite direction. So this direction of the phi is positive increase. The way we have put the coordinate x and y, and the phi is a point on the wheel. So that's why it's easy to make a sign error here, because you got to see in time how things are changing. Okay, so this is the case. Now we can divide by delta t. Divide delta t. See, now this constraint is constraint in rate of change. It's not like this kind of constraint. So this is kind of already in a velocity constraint. So angular velocity of the wheel is equal to times r is equal to the linear velocity of the second mass, the way we have laid this out here. Okay, so this will be r phi dot equals to y2 dot, and from here I can say r phi double dot equals to y2 double dot equals to minus y1 double dot. So I can just do phi dot double dot equals to minus y1 double dot over r. So we can get rid of this guy over here and put a minus sign, and y1 double dot over r, and one of these r's I can cancel out for this, so we just got one r left. Okay, so now we have this constraint leading to this, and so just write down phi double dot equals to minus 1 over r y1 double dot. So now this is given, will be given, because this is the force I need to be given. All m's are given, and from here we have unknowns. Number of unknowns is, let's count them. So in 1, 2, and 3, the unknowns are 1, 2, and 3. 3 knowns and 3 equations, so it can be easily solved, right? Let's solve them. Actually, this is already solved here because everything else known here except this is the case. So y1 double dot is 2 Okay, so how to solve for these unknowns? Clearly, if you add all of these up, then the t's will not cancel, right? So if you add this up, so I'm going to have to multiply this. I multiply this with a minus, then this will cancel that, this will cancel that, and on this side I'm going to have a minus m1 plus m2 plus half m, and on this other side I'm going to have m2 minus m1 g plus tau f over r. So this is the frictional torque at coming from the axle over there, and so y1 double dot will be divided by this. This is m1 minus m2 g minus this average frictional force, so to say, divided by the entire thing m1 plus m2. Interestingly, because of rotation, in the disk thing, the formula half comes from this half comes from. So this is now this solves the problem, right? So this is, I have again y2, and then I can get angular acceleration as well. That's a pretty interesting. You have from here, you can do, okay, I don't want friction, so no frictionless. Well, just set this to 0, and then this formula just becomes m1 minus m2 g and m1 plus m2 plus half m. You say, hey, I also don't want pulley to have much mass. Massless pulley. This will go away, and so you'll have a much simpler formula for y1 acceleration. And there you have it. Okay. Even when you don't have pulley mass, etc., you can still, from here, you can see that this will be minus y2, and this will be equal to minus r phi double dot. And so you can see even for massless and frictionless pulley, you can study the rotation of the pulley if you carry out this whole rotation problem along with the translucent problem. Okay, so there was some gaffe about this missing out in some parts of the video, but the rest of them is still okay. All right. Okay, so we have solved this problem, and you can just integrate it and things like that to get your y1 of t, y2 of t, and phi of t. Okay, so these things you can get it, and they all refer to this coordinate system. And so we're done. The problem is done. And you can say, well, how about that three pulley system you went in the beginning? Now, I just looked up, actually, it's already a very long video, like 35, and I'm a little bit tired right now. So I will do this three pulley system in another video, maybe next time, maybe I'll do it tomorrow. Okay, so for now, if you can check out my website, and you can also, if you like, hit the like button for this. I'll appreciate it. Take care. Bye.